Hi guys, I'm going to I'm going to talk about the Deligne-Illusie. First, this is the first video in a series of videos about the Deligne-Illusie theorem, and I guess the underlying goal, right, is to show a certain equivalence of the deformation arithmetic deformations with this as we've seen on the channel, that these arithmetic deformations, they're going to be like a gerb, so-called gerb, and we're going to show an isomorphism of gerbs to certain splittings. Okay, and so these have to do with certain Frobeniuses, and it has lots of applications. So let me give you the setup. Okay, yeah. So we're not going to prove the full theorem in this video, but we're going to prove parts of it. Okay, so we're going to have X is going to be a scheme over K. It's going to be smooth. And K is going to be a field of characteristic P. Okay, and S is going to be spec K. Okay, and for this video, we're going to use pretty much everything. Well, okay, we're not going to use quite the gerbs yet. In this next video, we're going to use the gerbs. But here we're going to use derived categories. So if you haven't seen those, see those. We're going to use the Cartier operator. We're going to use lifts of the Frobenius and P derivations. And what else are we going to use? I think that's about it. I mean, that's a lot of things that we've done, but that's what we've been building for. Okay, so this is what we're going to do. Okay, and I want you to recall that we have the relativization, we have these relative Frobeniuses and the absolute Frobenius, and there's a video on that if you haven't seen them. So go see those things if you haven't seen them. Okay, and so now I'm just going to start with this setup. So definition. So a derived Cartier isomorphism operator slash isomorphism, okay, is a morphism. So it's actually a quasi-isomorphism of complexes, but a morphism in the derived category of the following form. It's an isomorphism between this degenerate complex here. So we have this relativized Frobenius, and then we're twisting it here with this guy here. Okay, so it's a morphism, it's an isomorphism such that when I take cohomology, I get the Cartier operator for all I. Okay, so I want to show, first off, that this can make sense, and I want to talk about the shape of this. So what we're going to be proving is we're going to be proving existence of these things, and then we're going to be talking about like classes of them, okay, and there's going to be lots of them, one for each deformation or lift from characteristic P to mod P squared, from mod P to mod P squared. Okay, so so this is the situation. So let's recall. So this is a morphism here. So let me say that this is a d mod OX P. So this is modules here. We can say quasi-coherent modules if we want. And then this is an abelian category. So I guess you need to make sure that you're working in a category here where your quotients, so where you have quotients and you have limits and things, so that you don't fall out of the category by, say, taking a quotient of things that aren't necessarily, an object of the same category. Okay, so let's just say stick with modules. Okay, so recall if A is an abelian category. Okay, we can look at, so there's this map here from A to the derived category of A, right? Given by taking a single guy and we map it to this complex here, which is concentrated in degree 0. So this is the degree 0 piece, and we just make this complex, and this gives an embedding here. Okay, and if we have an object here, then we also talked about how when we twist backwards and we take cohomology, we're going to get our guy back. Okay, and so when we take an object in our abelian category, we're gonna sometimes identify it with this complex without saying anything. And this is what's kind of going on here. We've identified it and then we've shifted it. Okay, this is, I guess, shifting to the right. Okay, so here, the last thing that I wanted to say is that in the abelian category, if we have a bunch of objects here, it's a direct sum of things. In the derived category, we can break up Rhams like so. So this is going to be useful. In particular, we'll be able to decompose this term by term. Okay. Okay, so as a consequence of the remarks, so it's enough to understand, from a single piece. So we fix a piece here, and we're going to take a map into here. Okay, so, and then here, we can see that when we taking cohomology, we can see it's potentially a Cartier operator. We can see that it has the right shape. Okay, so we take cohomology here, and HI of this guy, of omega P over S, so S is again spec K, minus I here. And so this is equal to just the thing itself. And here we have HI. So in the previous videos of the Cartier operator videos, I was writing this with an underline, but we're not going to do that here because it'll just be really slow. Again, this is the relative Frobenius. Okay, so maybe sometimes I'll write this with a subscript R. I don't think I'll do that, but if I do, that's what I'm doing. Okay, so here, so this is this, and you can see, this is an I, that this actually has the shape of the Cartier operator. Okay, so this has the correct shape. So it's conceivable for something like this to actually induce a Cartier operator. Okay, so we're going to give a basic construction in this video. So like kind of a fundamental construction. Construction of Deligne-Illusie. Okay, and so this is a theorem. So suppose that these deformations from x to k to say the p-typical truncated width vectors of length 2 is not empty. I.e. the obstruction vanishes. Obstruction to lifting. Vanishes. Okay, so there's a cohomology class in H2, which we've talked about in other videos, which describes when there exist deformations here. And so in particular, we're going to look at smooth deformations. Okay, then for all deformations, P1, okay, we can associate some derived Cartier operator. Okay? So there's going to be a functorial, well-defined thing. Okay? Sometimes this theorem is described as the existence of an isomorphism here. But I want to emphasize the construction. Okay, so not only does it exist, there's kind of a procedure for doing this. Okay, so let me start a lemma. So it's enough to show a Cartier operator. It's enough to give a Cartier operator in degree 1. Okay, so here, what we mean by this is we just want some guy in the derived category. Just we need to show the existence of this guy. And so this will actually land in, so this map land in okay, so we could take the target to be just the first guy. Okay, so proof. Okay, so we need some ingredients. Okay, so the ingredient is the anti-symmetrization map. So omega I of x over s. So this is actually quite general here. So I don't need to do this. This is the top wedge power of omega 1. Okay, and so there's a map from A from omega I x over s. And so again, this is not specific to x over s, or to this complex here. Here to the tensor power omega 1 to the ith power. And what it does is it takes, let's say, omega j1 to omega ji, and it maps it to, it's like anti-symmetric, associated anti-symmetric tensor. Like so. All right, from here to here. Okay, so so there's this ingredient that we're going to use. So now we suppose that that there exists some guy, some lifted Cartier operator in degree 1. So we're going to do this. We're going to suppose from here. Okay, so this is just a morphism of complexes. Okay, so this one's shifted over to the right, and okay, and that's all there is to it. So that being said, okay, I guess we can just say something else about this. So this means that when you take the HIs, right, that you're going to have this, and this is going to go into cohomology of this, okay? So that's another thing. So this is equivalent to giving a map from here into here, right, which is well defined in cohomology. Okay, so we have this, and now let me say what we're going to do with this. Okay, so we have this guy here, and we have well, okay, first of all, let's take well, I don't know what order I want to do this in. Let's do here, x to the p over s, like so. So this guy has a section to, let me do this with tensor to the I. Okay, so there's this anti-symmetrization functor. So here, there's this guy A that goes from here to this tensor to the I. So ignore that for a second. Okay, so but here there's also a map from here. So if I take -1, so this is a functor. Okay, and here I can take a C1 inverse tilde tensor to the I. And I can take it here. Okay, and then I can go back down to this guy, so x over s, by taking the wedge powers. Okay, and so this defines, so this gives our map. This is our map that we want. Okay, so so this is how we define it globally. So I guess there's something to talk about with whether or not these tensors commute. The twist of the wedge power is the wedge power of the twist, but I'm going to omit this. Okay, okay, so that's that. Okay, so now there's some examples. Actually, let me do examples on a new page. So now we're going to do some examples of how to define it. So we need to define it in degree 1. The first example is suppose x tilde has a lift of the Frobenius. It's equivalent, so having a lift of the relative Frobenius is the same thing as having a lift of the absolute Frobenius, and they're interchangeable. Okay, so let me do it in this case. So, okay, so we're going to show the derived Cartier operator, and it's pretty easy. Okay, so here, proof, and then I'm going to give a definition after this. So x tilde has, let's say, so this is a pair of the lifted scheme and lift of the Frobenius. Okay, so we get a map, a morphism of O of x to the p modules. So I'm going to take this to be the relative Frobenius, p inverse. So here, when we take a differential, right, and we pull it back by a lift of the Frobenius, it's going to be divisible by p. And so what we can do is we can first do this and then divide by p, but when we divide by p, we have to mod out by the annihilator of p, and since we're working mod p squared, we actually get a map here. Okay, so this is this guy here, actually, this induces the C inverse of C inverse tilde. Okay, so recall that that having a map, so the -1 -1 to here is the same as, so this guy here, a map here is the same as a morphism So it's the same as a morphism like this. Okay, and this will induce the Cartier operator here. And so let's say this. So suppose so f tilde here. Let's say sharp of some section looks like, so note, this looks like f to the p plus p delta f. Okay, mod p squared. Okay, this is a p derivation. And 1 over p, so then d f tilde sharp of f. So what does this look like? This looks like 1 over p. So then we have p, f to the p minus 1, df, plus d pd delta of f. Like so. And this becomes f to the p minus 1 df plus d delta of f. Okay, so in particular, this is closed. Okay, and this is exact here. Okay, this may change as we change the lift of the Frobenius, but this thing is the Cartier operator, and this is closed. So let me actually come back here and give it definition. So this thing here, an operator like this, is going to be called a lifted Cartier operator. So I turned on some more light. Okay, so let me give another example. Example B. Okay, so there's two examples. This is the first one. The second one is the case where suppose x tilde has 2 lifts of the Frobenius. Let's say f2 tilde. So we claim that so P inverse and f2 tilde give the same operator, same derived Cartier operator. Okay, so that they're the same morphism in the derived category. They're homotopic. Okay, so let me give a remark here, and then I'm going to pause the video and then make another video real quick. So we are going to use the fact that p derivations are a torsor under Frobenius derivations, under the derivations of the Frobenius. So maybe this is the absolute one. This is the sheaf of derivations here, and this is maybe another way of writing it is that this is like the Frobenius linear derivations. Okay, and okay, so let me do this real quick. So I stopped the video to talk about the torsor structure, and so I just did that. So here we have that this is so we have that the p derivations. So the p derivations from say on O of x1 to O of x0. Okay, so these are p derivations from here to here. Our tors are under the absolute Frobenius like this. Okay, so that being said, I can use this, and it's just the simple difference. The difference of two things is going to be a p derivation, and so then we actually, so this is, let's say, from x tilde, in this notation of this video, x tilde to x, and then this is a derivation in characteristic p. Okay, so so now what we can do is, we wanted to show that these give the same derived Cartier operator, so let's take the two guys and we'll subtract them. And this defines a map here. Okay, and so we want to describe this. Okay, so let theta equal the difference of the two p derivations, right? The difference of the two associated p derivations. Okay, so that here, so this is what we'll write. We'll write that fi tilde sharp is equal to, let's say of x, it's going to be x to the p plus p. So I'm writing this in terms of the absolute Frobenius right now. Let's say delta I, for I is equal to 1, 2. Okay, and then so this guy would be equal to delta 1 minus delta 2 mod p. Okay, so we take the difference, and it's, I mean, I guess we don't need to define it mod p since it's already defined mod p, but here, this is what we have. Okay, so we have this. All right, and so so notice that here, so so this guy here is an element of derivations on O of x. Okay, this is the same thing as I said up here. This pullback here. Okay, and so this gives us this induces some theta prime. So I'm gonna write theta prime to be the associated thing for the relative Frobenius. Okay, and this is equal to the same thing as morphisms here to O of x. Okay, and the map here, we'll call this map from theta prime. We'll call this map here h theta. And what's the description of this map? So this is kind of a cup product or inner product, but I'm going to call it cup product with Deligne-Illusie. Okay. Because in the case where we're going to have a bunch of, when we're going to be gluing things together, this will actually come from a cohomology class. Okay, but it's actually just the thing where we take a differential form and we pair it with our operator here, and that gives us this map. Okay. So lemma, in the notation we set up, so F1 sharp minus P2, P inverse F2 sharp is equal to dH of theta, where theta, okay, is equal to, well, so there's two ways we can say it. 2 sharp divided by P this is equal to delta 1 minus delta 2 divided, or just delta 1 minus delta 2. And this is a derivation of the Frobenius here. Okay? So this is we're using the torsor of lifts of the Frobenius structure. Okay, so the proof is simple. It's just a basic computation. So recall that here, applied to some df, this looks like f to the p minus 1 df plus d delta I of f. And so this is the p derivation here. This part here is the p derivation. To f sharp. So just the delta I is. So this is the p derivation. Okay, so now we can just write this out. So this is d of the difference of these guys. Okay, and so this is d of theta 1, 2 of f. Okay, so theta is equal to theta 1, 2. Okay, and so this is d of, now we have this theta 1, 2 paired with df. Okay, and this is what we call d of h of theta 1, 2 of df. Okay, so this shows that these two maps here are cohomologous. Okay, so we showed this for every local section F.